Okay, so the problem set 1 is posted. It's due a week from Monday. So it's due Monday the 4th. And it looks like something like this. Ooh, look how skinny that gets. And I don't know where the loads are. There's a, although it does tell you on the assignment. So don't worry about that. There's a roller there. Okay. And so the assignment is to calculate the internal loads, basically. First you have to get the external loads. So calculate the internal loads along that, internal loads along that, and internal loads along that. So those are the two different lines I meant. So when you do it, you'll have to figure out what the loads are at this fixed joint, so that you can go, from one to the other one. Okay. There's no torsion on any of this because I couldn't figure out how to put it in without messing up other things. So I'll keep working on that for next time. Anybody have any questions about that?
Is that the first example we're doing today?
No.
We came in on a Friday, though.
That's holding yourself to a very low standard. Yeah. That's right. We're better than them. Okay, so when we calculate, so moving on, stresses in beams. The total stress tensor is equal to the stress tensor due to tension plus the stress tensor due to the bending moment plus the stress tensor due to the shear force plus the stress tensor due to torsion. We're done with this one, and so we're just going to keep going down the list. So the next thing we're going to talk about is stress due to torsion. No, not correct. Stress due to shear force. Yeah, why would I have done it in that order? And then it's really disconcerting when you are thinking something and then you notice your mouth said something else. Have you ever gone to write something and your hand just writes something totally different? Like you go to write like a Q and your hand writes a 4 or something? Yeah, right. I don't know. All right. So what was the first thing that we talked about when we talked about stress due to bending? What was the first? No, don't do that. Don't do that. What was the first thing that I brought up? Okay, but before, so yeah, we did the 2 mathematical preliminaries, and I'm going to do that here too. But before that, I said it was even more important than knowing how to do the calculation was understanding under what conditions. Yeah, so the rules for when it applies. And it had to be straight. That was one of them. It had to be symmetric about the y-axis. And is that all?
Prismatic.
Prismatic, right. It means that it's the same cross-section the whole way along. Okay, so now we're gonna start shear force doing that too. So beam requirements for shear force calculations. Well, sorry, let me make that more clear. For calculating the stress due to shear force. So when we're doing calculations with shear force, we have a lot less flexibility in what kind of beams we can look at than we did with bending moments. So much more stringent requirements. Than stress due to tension or the stress due to bending moment. So here are the requirements. We can only calculate the stress due to shear force for two cross-sections. Two cross-sectional shapes. The first one is rectangular cross-sections. It's most accurate for heights of cross-section that are bigger than the width, than the base. So I'll draw the cross-section here. So you can get good results for a shape like this. But shapes like this, even though it's rectangular, the approximations that we're using aren't going to be very good. And the second cross-sectional shape that we can deal with is circular, but for circular cross-sections, we can only calculate the stress due to shear force along the center line. So we can only do it along one line. We can only calculate it, I guess a better way to say it is, along the neutral axis. Okay, so that's only for the circular cross-section. In a rectangular cross-section, we can find stresses anywhere on the cross-section. For a circle, only here. So that seems absurdly useless, except that that happens to be the place where the stress due to shear force is maximum. So at least we have that. Like if we're trying to figure out where you're going to get big stresses due to shear force, we can calculate that for a circular cross-section. So that's where the biggest stress due to shear force occurs, at least. And one thing to keep in mind as we go through this,
What's the difference between notice and keep in mind?
I don't know. I was going to say notice, and then I was like, well, I haven't showed you anything that you could notice this from yet. So this is just, I'm introducing something now for you to remember. And that is that in bending, the maximum stress due to bending is at the top and bottom of the cross section. With shear force, the maximum stress due to shear force is always at the neutral axis. So if you're dealing with a beam that has both bending moment and shear force, and you're trying to figure out where the total stress tensor is going to be biggest, now there's sort of this complicated interplay between these two. You have to deal with the possibility, can you understand what I'm talking about? So if, no. Well, the stress due to the bending moment is smallest, it's actually 0 at the neutral axis, but gets bigger at the edges. The stress due to shear force is biggest at the neutral axis and drops towards 0 at the edges. So if you're looking for the biggest combination of those two stress tensors, it's a little complicated to figure out where it is.
What is the correlation between the edges and the middle?
I think the answer is it depends on what the magnitudes are of the two things. Mm-hmm.
You think that the shear force would be the same throughout?
Yes. It does seem like I could see how you would think that. It's not popping into my head right now like really an intuitive way to explain that. But I'll think about that, and if anything comes up, I'll mention it. Any other questions?
Is like the bending and shear due to the same forces? Like, or is this like...
Well, yeah, I mean, because, the dm dx has to be equal to v. So they're related in that way.
Okay.
But you can have bending without shear, and the effect of the shear as you go along the beam is different, So yeah, they're right, because you have that negative Vx term in your internal loads calculations. So as x gets bigger, the shear produces bigger bending moments. Okay, so the first mathematical, well, actually, I think the only mathematical preliminary, EQ over, yes. Okay, so mathematical preliminary. This is what I will call Q1. And here's how you calculate it. Say this is the cross section. This is just an arbitrary cross section. You can calculate this Q for anything. And let's say this is the neutral axis of that cross section. What does the neutral axis mean? Yeah, this is so if you bent this thing, that is a cross section of the sort of plane that would stay the same length as you bent it. Anything above it If you bend it like up, anything above it would be getting shorter. Anything below it would be getting longer. And so let's say that this is the line, let's call that Y1. Then this area is A1. And if you find the centroid of this area, so that's the centroid of A1. And take the distance from the neutral axis to that centroid. Call that D1. Then Q1 is equal to the area shaded in red times that distance D1. We haven't talked about it yet, but it's going to come up in the formula for the stress due to shear force. Okay, so can this be negative? Nope. It's an area times a distance. So, okay, this is the area of the region above Y1. And one thing that's, okay, this is another place where I could have said notice, but I'm going to call this a cool factoid. If you calculated the Q1 above that line Y1, and then calculated Q the same way below, you'd get the same thing. So to do it below, you'd do the following. Should have made this an easier shape to copy. Okay, so here's your line Y1. Here's your neutral axis. So this time, calculate this area. The centroid of that region, okay, so that's, call that A1. The centroid of this region is here somewhere. Then this distance is D1. And this, just mathematically, has to be equal to this one. So when you have, once you choose a line where you're trying to calculate this Q, it's up to you whether you want to do it by taking the area above and the centroid of that, or the area below and the centroid of that. Sometimes one will be easier, sometimes the other one. So you have two options. Okay, so let me do an example. So let's say you have a rectangular shape. And the base is 0.5 meters. The height is 1 meter. So where's the neutral axis for this shape? Oh, and I have to choose a y1. So let's say that y1 is 0.8 meters from the bottom. And we want to calculate Q. So where's the neutral axis for this rectangular cross section? Right in the middle. Okay, so
That doesn't like depend on where forces are being applied and stuff.
where the neutral axis is? No, the neutral axis is always parallel to Z, and it always goes through the centroid of the cross section. Okay, so this is our line y1, so this is the area we want. And then the centroid of that area is here. So the area is equal to, what's that, 0.5 times 0.2? So 0.1 meters squared. And this distance, what would that be? So that would be, yeah, 0.3, and then, right, 0.4 meters. And so then Q is equal to 0.4 meters times 0.1 meters squared, so 0.04 meters to the third. So SI units for Q are always going to be meters cubed. Okay, so that's the only new mathematical thing we need. And now we can talk about calculating the stress due to shear force. So let's talk first about what happens. So if this is the point on a beam that you're looking at, and so this would be your base, this would be your height for trying to figure out how good your approximation is going to be. This would be your line of interest represented by this infinitesimal strip. Your shear force is this. And that shear force is generated by a bunch of infinitesimal downward forces like this, and those determine what the stress is due to that shear force. So these show the direction of stress on, you can say, the right side of a line of stress elements. Like you can think of this infinitesimal strip as being a bunch of stress elements lined up side by side. Like here's one next to it. So, based on that, if this is, so if your coordinate system is this, because this is what we always use for beams. What element of the stress would be produced by that shear force? It's a shear because it's happening on the x face of these stress elements, and it's in the negative y direction. So a positive shear stress leads to a positive shear force leads to negative values of the xy stress. Like if you blew one of these up, one of those stress elements up, it would look like this.
That's how XY might be used to be seen as sigma XY.
That's right. Yep, those are interchangeable. So tau is what people use that when they're talking about shear stresses, or you can just use this. Negative, yep. Okay, and the calculation is like this. So tau xy is equal to negative v times q over ib. Where b is the width of the cross section, at the desired location. I is the area moment of inertia. So that's the same one we use for the bending moment. And you can trust the sign for this formula. So if you have a positive value of shear force, you're going to get a negative value of the XY stress. You know, if you have a negative shear force, you're going to have a positive value for the XY stress. Okay, any questions about that? So let's do a calculation. So say we have a cantilever beam that's 2 meters long with a mass of 100 kilograms. And let's say that we want to know what's the stress tensor along this line. And if we look at the cross section, it looks like this, where let's say that's 0.1 and this is 0.02. And this isn't enough information to decide where we're going to calculate this stress. So let's also say if that's the neutral axis, the line of points where we want to calculate stress tensors is right here. So this distance is 0.025.
Sorry, that's D. That's D then.
What?
Is it
Oh, no, that's not D because we're going to have to, so D, we're going to take the area here, find the centroid of it, and then calculate the distance from the neutral axis to the centroid. Okay, so what's the stress tensor at the red line? We have to calculate the internal loads. Usually we calculate the external loads first, but we can get by without doing it here because this is a cantilever at the right end. So let's just go right to a cut, and instead of calculating the internal loads for every x value along the beam, let's just do it at the one place that we care about. So we'll do a cut that represents x equal to 1 meter. Where the rest of the beam is over there. Okay, so what loads are acting on this left half of the beam?
Weight.
Okay, and how much weight is acting on it?
50x.
That's right. It's 981 is the weight. That's the mass. But, yep, that's the right way to think about it. So it's half the weight. And we don't have to. So normally we would do it as a distributed load and then treat it as the distributed load times x. You'd get the same thing if you did that. But in this case, since we know we're taking half of the weight, we'll just call it 490.5 acting right at the middle. Anyone confused about that? Okay. And then the only other loads are tension, shear force, bending moment. There's no torsion here, so I'll leave that off.
So it's not 490.5x.
Okay, let me do it the whole way. Too late.
We already know that. Yes, 490x.
That's right, yeah. So it's a distributed load of 490.5 newtons per meter. They're the internal loads. And now that we've chosen the body to isolate, we can write that as a point force. We know that this is 1 meter. So you have a point force of 490.5 and internal loads. Okay, so Newton's second law says 0, negative 490.5 plus T negative V is equal to 0. So there's no tension at the point that we're looking at. And the shear force is equal to negative 490.5. And then the bending moment, our about point is here. What's the moment arm for that 490.5? Yep, 0.5 times 490.5, and would that produce clockwise or counterclockwise? Yep, so that's negative. And then we have plus m minus Vx is equal to 0. So m is equal to Vx plus 245.25. So m along that red line is equal to negative 490.5 x. Well, I said x, but we know that x is equal to 1. So negative 490.5 plus 245.25 is equal to negative 245.25. Okay, I have one question. It's sort of a math question. So how does it work out that if you take the derivative of m here with respect to x, you don't get v? What's the deal? Yeah, that's right. So we're only looking at point values here. If you did this and calculated m as a function of x and v as a function of x, those functions would have to meet that criterion. Okay? But since we just did it point by point, there's no way to check that. All right. So now we have to calculate the stresses. So the total stress is equal to the total stress due to tension plus the total stress due to bending moment plus stress due to shear force plus stress due to torque. We don't have this, and we don't have this. So we just have to figure out what the stress tensor due to the bending moment, the one due to the shear force, and add those together. So let's do bending first. Well, we need to calculate the area moment of inertia. So that's equal to 1/12 times the base times the height cubed. Can someone calculate that for me? Okay. And what are the units? Yep. And so the XX stress due to bending is equal to negative my over I. So that's negative. M is negative 245, so negative 245.25. What's Y for this? Yep, 0.025 is Y. That's different than that distance that we're going to use to calculate Q. Yep. And then divide by I, 1.6667 times 10 to the minus 6th. And what do you get for that? 3.68 times 10 to the 6th. And that's pascals. And so the stress tensor due to bending is 3.68 times 10 to the 6th, zeros everywhere else. And now we'll go to the shear force. Okay, so we already have I. We need that for the shear force calculation. So now we just need to calculate Q. So what's Q for this line? Well, it's equal to the area above that line times the distance to the line. So what's the area? Oh, right. 5e to the minus 4. 5 times 10 to the minus 4 meters squared. And then what's that distance? Where is that? 0.0375 looks right to me. Okay. So the distance that we want is from the neutral axis to the centroid of this. So the centroid, this whole orange shaded region, has a height of 0.025. So half of that is 0.0125. And then we're adding it to the other 0.025. And what do you get if you multiply those? Okay, and that's meters cubed. Okay, let's keep them all. Okay, so the shear stress, the XY shear stress, is equal to negative V. Our V is negative 490.5. Times Q, so 1.875 times 10 to the minus 5, divided by I. What was that? 1.6667 times 10 to the minus 6 times the width of the base, so that's 0.02. And what do you get from that?
235,906
pascals. So the stress tensor due to shear force is 0.275906, 0, then 275,906, 0, 0, 0, 0, 0. So the total you get from adding those two up, and that is 3.68 times 10 to the 6th, and then I'll call this one 0.276 times 10 to the 6th, 0.276 times 10 to the 6th, Any questions about that? Okay, so then once you have that, you can calculate the principal stresses. This is a complete stress tensor. That's all that's contributing to stress at that point. So you could use this stress tensor to calculate the principal stresses, and then use that to calculate the max shear stresses, and get a good measurement, good calculation of how likely this is to break there. Another thing you could do is you could do this calculation. So if you wanted to see where on this beam you were most at, okay, so say we've chosen this point A to analyze, but we want to know where on this whole cross section, say, this is most likely to break. You could do that calculation while keeping the y value as a variable, come up with an expression in terms of y, and then maximize that value when you get all the way to the end. But I don't think I make you do that in any of the problems I remember.
Are we going to be doing any with circular shear?
Yes, so we will, and then anytime you have a circular cross section, you don't have to worry about calculating bending at all, but what you will have to worry about eventually is, for circular cross sections, we can do torsion calculations. So if you have like something with a circular cross section, it can have shear forces and torque on it, and then you can calculate the total stress along the neutral axis for that. Only circular or thin-walled tubes. Thin-walled tubes can be any shape, like if you imagine like an aluminum pipe or something. But for solid shapes, for torsion, yeah, we'll only be able to deal with circular cross sections. Any other questions? Okay, that's it.